In this video, we're going to be developing kinematic guidance models. And again, remember that we refer to them as kinematic when we don't directly consider the forces or the moments acting on the aircraft. We're going to start off with Dubins' model, which will be used in the following chapters for planning. We'll then develop a series of models that increase in complexity. First, we'll look at a model that considers near-level flat-winged flight. Then we'll introduce the coordinated turn model for larger bank angles. And then finally, we'll introduce the flight path angle for non-level flight. So let's go ahead and get started. Like we mentioned, the first model we're going to be considered is known as the Dubins model for path planning. It ignores wind. It assumes a coordinated turn model. We have a constant velocity, and we have and when we say constant velocity, we mean that our VG dot is equal to 0, right? So we're not going to be changing our ground speed velocity. And we're going to assume that convergence to the commanded values is fast compared to the rate at which the command is being changed, right? So we have this pass-through for our commands. So this ignores some of the models that we developed in the previous video. All right, so let's first talk about what's called the Dubins airplane model in the book. It doesn't include the aerodynamics, wind effects, or engine thrust or limits, but it is, let me highlight this is well suited for high-level path planning and path following control design. And that's what we'll utilize it for. Okay, so if we start to look at this, we see these three elements are the time derivative of our north, east, and down positions. These were just taken from our wind triangle relationship. Where since we're not using, since we don't have any wind, we could have replaced these with gamma as well, right? So just to know that that's our gamma commanded. Sorry. So we have our flight path command, right? That we're commanding, and we're just assuming that that's going to be immediately realized. So that's our pass through. And then for our turning, we have this model. This is our just directly taken from our coordinated turn. Okay. The inputs to our system have bounds. So we have bounded inputs. And this should have probably had a superscript C. But we have if we look at the states of our model, what we're going to do is we have our position states, PN, PE, and PD. We also have our heading. And then the inputs to the model are just going to be our commanded roll angle and our commanded flight path angle. So those are the direct inputs, and we're assuming that, again, there's a pass-through, so it's quickly responding, and we get these nice relationships. And the only real condition we put on our inputs is that they're bounded between a maximum and a minimum value. Okay. Again, because we assume that VG dot is equal to 0, right? VG pops up here, and I guess here too. This is just VG is constant. So it's just a parameter in this case. Okay. This is modified from the original Dubins model, where we could express our northeast and down as VG cosine of our heading, VG sine of our heading. And we're going to be directly controlling the time derivative of our heading. So we directly control our down and the time derivative of our heading. Or even slightly simpler, we could assume that Pn dot Pe dot is equal to Vg. Oh, we could have it as U1 cosine phi sine phi, and then phi dot is equal to U2. So assuming that we don't have any down position at all. So this is our Dubins model, and what it does is it nicely accounts for that nonlinear, non-holonomic component of our position derivatives. Okay. Up here in this model, this modified model with the airplane, we can actually take into account a higher fidelity of when we have a flight path angle. Okay, so this is our Dubins model. Again, we've listed our states and our inputs to the system, and for planning purposes, we'll just assume that those are the only states and inputs that our system has. Okay. All right, so now let's jump into these other kinematic guidance models, and these ones are going to be developing or utilizing some of the autopilot command models that we presented earlier in a previous lecture. So if we look here, let me go back to blue. These bottom three equations are just our autopilot models. As our first and second order models. Okay. Then we have our position, right? So this is assuming we have near flat level wing flight. So in other words, we have our gamma terms, which we could see here with this cosine of gamma is just equal to 1. So we don't have to worry about that. Well, I didn't need to really erase that. Okay. So if we come in here, we do have wind in the northeast direction. So we can say that we have a bit of wind in the northeast direction. So the wind is just disturbance to our system. Okay, so if we were to look at the states of our system, we end up getting Pn, Pe, we have chi, we're going to have chi dot since it has the double dot in there. Same for height and height dot, and we have also Va. If we were to look at the inputs to our system, we have our commanded course angle, our commanded height, and our commanded airspeed. So this is a full model for our system. We're going to look, if we look here, we have this relationship where we have our heading angle as forms part of our derivative. Well, this is just this highly nonlinear function of our flight path angle. Oops, not our flight, our course angle. I keep getting those mixed up. Our course angle and our airspeed, and again, here's our course angle showing up. So we have a nice nonlinear model, but we've used the first and second order models, assuming that we have the commanded course angle, height, and airspeed. Okay, so we can take this model, and I want to emphasize that we're assuming near flat level wing flight. Okay. And again, this model would also assume that gamma is very small for this guy right here. Okay. No, that didn't have anything to do with gamma. Sorry, that was a note for what I just barely highlighted. Okay, now we have our first variation of that. So we say that this was our model 1A, and this is model 1B. And it's just a slightly simplified model. And what we're going to do is if we assume no wind, so we should actually cross these two things off, then what we've done is, if you see, we've just replaced our course angle with just our heading angle. So this is the main difference between the models 1A and 1B. Okay. Again, these three models were developed, or three equations, were developed previously from our autopilot models. So these are autopilot models. Excellent. PN and PE are nearly the same as they were before. We have just this one simplification. So we just have this one simplification. Which is really nice because then we get rid of that hairy relationship. Okay, so let's just one more time. Let's write down our states and our inputs. And just take a second to make sure you can write down all the states and inputs yourself. Okay, so hopefully you paused, wrote them down. We have north, east. Now we'd have psi dot, h dot, and VA. So just keep in mind you have to have two states if you have the second derivative in there. And you have the actual, well, the state itself showing up. So we have two states for both psi and h because we have the second order dynamics. And then we'll have our, taken as our inputs, we're going to have our heading angle command, our height command, and our airspeed command. So we're assuming those are the inputs to our system, and then this is a good a decent kinematic model. Again, we have the assumption of no wind, and we're going to also have near flat level wing flight. So we have all those assumptions that we need to make sure. If those are appropriate, then we could potentially use this model. Okay, let's move on to our second, really our second classification of models. And what we're going to do is we're going to introduce our coordinated turn. Again, the book, I've realized we didn't need this term, right? So we have our coordinated turn model, and that's what we're introducing here. So we have our coordinated turn. And right here, we have, again, our autopilot models. Excellent. So the position, the model is exactly the same as before. Let's, again, write down states and our inputs. Take a pause. Make sure you can write them all down yourself. So we'd have PN, PE, would have psi, h dot, and we have VA, and we have phi. So a couple things to note is now phi is one of our states, right? And we do not have no chi dot, right? I think I said psi when I was writing it down. No chi dot. Okay. So the inputs to this system are going to be our height command as before, our VA, our airspeed command as before, and now we're saying that we might have a commanded roll angle for the inputs. Excellent. So this one, we still have little vertical motion, i.e. our gamma is almost 0. Okay, so that's one big assumption we have to make. The other thing that the the other assumption we are making is that we are commanding our phi angle, right? But then we can use this coordinated turn model. We again have psi show up. So we have that same relationship as before. And one thing you'll note here is we also have VG show up, which we have another hairy nonlinear relationship there. So just as with model 1, we're going to assume that our wind is non-existent. So now we'll add in the assumption no wind, right? And because of the no wind, then our heading angle and our course angle are equivalent, and also the VA is equal to our ground speed velocity. So we have those simplifications, right? So now we have VA there, and we have our heading time derivative instead of our course angle derivative. Okay, so those are the two major differences. So again, if we were to use model 2B, we have very little vertical motion, so nearly flat motion, and we have no wind. And this no wind should cancel those two out as well. Okay, you should be able to look at what our inputs are. Our inputs are going to be the same, and our states are going to be nearly the same, except for the one change here where we're replacing our course angle with our heading. Okay, so that was our second kinematic guidance model. Our third model is we no longer assume that our flight path angle is approximately 0. So we no longer assume that. So this relationship here, we again get from our wind triangle relationship. Where we've now incorporated our flight path angle. And I should highlight that. That's what we're doing here. And because we're incorporating our flight path angle, we're no longer assuming that our height changes independently, right? And we're also adding in our flight path angle. So those highlighted changes are the main changes. We do again have our autopilot models that we introduced in a previous lecture. So if we now come in here and we write down our states and our inputs, you should be able to do this on your own, but and take a minute to do it. But we have PN, PE. Now we only have height. We don't have the second derivative, right? We have, in this case, we maintained it with our heading angle, right? Gamma, VA, and phi, with our inputs being, now we have a commanded gamma value, our commanded airspeed, and a commanded roll angle. Now, if we look at these equations, they're actually in terms of gamma sub A, so our air mass referenced flight path angle, where we have this nice relationship here. Okay. And we can use, again, these relationships here. This is an interesting model number 3, where we could have had our course angle as we started off with model 2, right? So we could have done our course angle instead of our heading and used those same relationships as before. Okay. Now, for our fourth kinematic model. So our last kinematic model, we're going to introduce that load factor. And so you'll see here we've got our flight path angle is a function of our load factor, and we have our load factor in there. So everything else is basically the same. Again, we have our autopilot models coming in here. And if we were to write out, do it over here this time since we have more room, states and our inputs, we have PN, PE, we have our height, we have our heading, we have gamma, we have VA, phi, and our load factor. And our inputs here are going to just be our VA commanded, phi commanded, and our load factor commanded. Okay, and apparently, at least the book talks about this being a convenient model, especially for pilots, as it relates a little bit closer to what the pilots are commanding in an aircraft. So we have this final kinematic model where we've introduced the load factor, and that load factor starts to jump into almost having an element of our forces included.